All right, guys, homework from Thursday due for today, questions 1 to 7 on worksheet number 3. The answers for the first 3 questions are up on the board right now. Have a peek. Don't worry about the solutions. We'll go over one if we need to go over it. Just look at the answers to make sure you got it right or to notice if you got it wrong. Question 4. And it's questions 5 and 6. Question 7, again, I'm not putting the answer up to that one because we're going over that one regardless. I don't even need you to see the answer for number 7 right now. We'll keep that a nice little surprise, and then we'll go over question 7 as a group here in just a moment. Let's take a peek at question 5 and 6 and see if you need either one of those ones gone over, please. All right, we're going to take a look at 4, 5, and 6 on worksheet number 3 then, and 7 on worksheet number 3. 4 says a 1,500 kilogram car traveling at 100 kilometers per hour south. A couple things to draw attention to that with our red colored pen or our ugly colored highlighter. Kilometers per hour because we like to be in meters per second. South because the whole north-south thing, something's got to be negative. Here's another car traveling north at 100 kilometers per hour. The heavier car continues to travel south after the collision, but slows to 25 kilometers per hour. How fast is the lighter car moving after the collision here? Let's record some givens here. Let's call this one M1, 1,500 kilograms. Let's call this one M2. The heavier car, remember this, it refers to the heavier car later on in the question. So let's remember that the heavier car, we're calling car number 1. That means that this one is going to be car number 1, okay? The heavier car continues to move south. This one is going to be V1I. Let's put in brackets here that's got to be negative because it's to the south. What about the kilometers per hour? Do I have to convert that to meters per second? I actually don't here. In conservation of momentum, there's very few times where you can leave kilometers per hour. Conservation of momentum is one of them. Now, if you're in doubt about that or you're just confused by that at all, then just go meters per second because it always works when you convert to meters per second. Always. Okay, there's never a situation where it doesn't work using meters per second. But you can use kilometers per hour here because in the end, the units kilometers per hour appear in every term of conservation of momentum. Because they appear in every term, they end up canceling. So whether you're using kilometers per hour or meters per second doesn't make any difference. In the end, if you divide it by 3.6 to get meters per second, then you'd be dividing every term by 3.6, which is going to give you the exact same answer, right? This one is going to be V2I. We're going to say V1F is 25 meters per second, 25 kilometers per hour, but we're going to make that negative, and we're looking for V2F. Listen, I've told you it's okay to circle things like this and identify givens this way, but if it gets too cluttered, and sometimes it does in these conservation of momentum problems because there's so many variables given to us, just write it out the old-fashioned way like we did in Physics 20, right? Write them off to the side. Okay? It's okay to take that shortcut, but we also want it to be helpful and organized. If it's all over the place and it doesn't make sense what we have circled, then just do it, as I say, the old-fashioned way. All right. PI is equal to PF. Now, in the end, each one of these cars experiences an impulse. We had a quiz on Friday, which remind me to hand back to you, by the way, today, where we analyzed the collision using conservation of momentum. But then we looked at one individual car, the impulse experienced by one individual car. We could do that here too. We could look at the impulse experienced by the heavy car or by the light car. But generally, in one of these problems where there's a collision, you have information about 2 cars. Generally, you're just going to look at them both as a package and use conservation of momentum. PI equals PF. 2 cars before, M1 V1I plus M2 V2I. 2 cars after, M1 V1F plus M2 V2F. Now, I'm going to save myself the bother here, and I'm not going to convert to meters per second. But if you did convert to meters per second, all you do is divide each of those terms by 3.6. Okay? 1,500 times V1I is 100 to the south. We're going to make that negative 100. M2 is 1,200 times V2I is positive 100. 1,500 times V1F is negative 25 plus 1200 times V2F. Get a number here. Okay, it works out to be, what, 15,000, 150,000 is it? Plus 120,000. So it's like going to be 30,000, I think, on the left-hand side. 1,500 times negative 25. That's negative 37,500 plus 1,200 times V2F. Let's take the 37,500 away, adding 67,500 divided by 1,200. And when I do that, I should get, let's see here, let me just check my answer here. I have it in meters per second, actually, in my answer key here. It's 1.74 meters per second, or it would be somewhere around 7-ish kilometers per hour. Anybody have it in kilometers per hour? 6.25 kilometers per hour. Now, if you wanted it in meters per second, you could either do it in meters per second from the start, get that as your answer, or you could just convert it to meters per second at the end. Doesn't matter. So 6.25 or 1.74 to the north, doesn't matter. Good. Number 5. 92-kilogram football player running at 6.5 meters per second to the north collides with another football player at 6 meters per second to the south. South, right? We got a south and north here. They're both north, okay? Doesn't matter. They're both positive. Even if they're both south, okay, if everything's going south, we can make them all positive. But if something's north and something's south, we got to make one positive, one negative. Draw attention to that. This guy continues moving at a velocity of 2 meters per second after the collision. Doesn't say which direction, but it does say he continues to move, okay, at that speed after the collision. So let's assume it's to the north. What's the velocity of the 85-kilogram football player after the collision? So this is going to be M1. This is going to be M2. This is going to be V1I. This is going to be V2I. This is going to be V1F. We're looking for V2F. So we're going to say PI is equal to PF. We're going to say M1 V1I, same as you did in the last question. It's M2 V2I. They don't stick together here. So we're going to have two terms after the collision as well. Don't forget the negative for the 6 there. All right, so what you're going to do, you guys, is solve for this, add them together. Well, subtract them, actually, because the second term is negative. Get this term, it's positive, take it to the other side by subtracting, and then you're going to divide that term by 85. And when you do that, V2F works out to be 1.13 meters per second to the south. Good? How many people got that one? 1.13 to the south. Okay, good. Is that okay, ladies? Number 6. All right, this is one of those explosion questions, right? The guy's standing on ice, not moving, throws a ball. Ball goes one way, he goes another way. Let's call the 75-kilogram man M1, and the ball is M2. Now, why do I not want to combine those masses? Sometimes we've seen questions where we've combined the masses in our givens and just called it M1 or M2. Guy on a skateboard throws a ball. Why did I combine the guy in the skateboard's mass, but yet here I'm not combining the guy in the ball's mass? When a guy on a skateboard throws a ball and the guy in the skateboard don't split up, when they remain one object through the whole question, then consider them one object, M1 or M2 as the case may be. Okay, but the ball separates from the guy. Okay, if it's the same object initially, that's fine, but it's got to be the same object through the whole question in order to call it one mass. Okay, we've got initially, the guy and the ball is one object, but then by the end of the question, the guy is separated from the ball. So we have to keep them separate here, M1 and M2. The ball gets thrown at 3.5 meters per second forward. That's going to be V2F, 3.5. We want to find V1F. VI, by the way, VI, guy standing at rest, 0 meters per second. So with conservation of momentum again, we could do impulse for the guy, or we could do impulse for the ball, but the easiest thing to do here, I think, is conservation of momentum. 0 initial momentum, because everything's at rest, is equal to 2 terms afterwards, M1 V1F plus M2 V2F. V1F is what we're looking for. Would you predict at 3.5? Yeah. Would you predict the velocity of the guy to be more or less than 3.5? Why did you say that, Bailey? Okay, just kind of intuitive. Okay. You're right, by the way. Anybody have a good reason why the guy would be less, Bo, than the speed of the ball? Yes. Yeah, he has more mass, right? The guy and the ball have to have the same amount of momentum to add up to give me 0, right? If they have the same momentum, but yet the guy is quite a bit heavier, to have the same momentum, he's got to be moving quite a bit slower. So let's figure this out. This term goes over by subtracting. It's going to give me 14. Negative 14 divided by 75 gives me negative 0.187. We knew it should be negative because the ball went forward. Guys got to go backwards. And Bailey and Bo both predicted that it should be a number that's quite a bit smaller than the velocity of the ball, which turns out to be. Okay. And finally, question number 7, the one that nobody really knows if they got the right answer for this one because I didn't show you the answer. I wanted to leave this one a nice little surprise. This is a good question. This is a challenging question. Okay, I know some of you weren't able to get this. The challenge with this one is not so much the overriding concept, which is conservation of momentum. Guy fires a gun, right? Bullet goes one way, the guy and the gun go the other way. The issue with this one is the frame of reference. You're on a train that's moving, and everything you have is relative to the train, but yet you want to find the velocity of the gun relative to the ground. There are 2 frames of reference here, and you have to pick one of them. You have to pick either the train as your frame of reference or the ground as your frame of reference. And it doesn't matter which one you pick. My suggestion, the way that I did it at least, pick the train as the frame of reference. Okay, so do everything relative to the train. Understand when you do that, you're not going to get this answer. You're not going to get the answer relative to the ground. We'll worry about that later on. Okay, when we do it relative to the train, we'll get how fast the gun is moving relative to the train, relative to the moving train. So in other words, pretend you're inside this moving train, the windows are all covered up, you have no concept that you're moving, and you wouldn't if you're moving at a constant speed. Okay, how fast does the gun move backwards relative to the seat that's underneath you in the train? All right, we're going to call this M1. We're going to call this M2. And we got a crazy unit there, grams. Be careful about that, right? Because we've got kilograms and grams. We want to make sure that obviously we're in kilograms there. The train is traveling at 75 kilometers per hour to the east. So right now, I'm going to ignore that because we're doing it relative to the train, right? Whether the train is moving at 75 or 7,500 meters per second, it doesn't make any difference if we're doing it relative to the train. That only matters if we're doing it relative to the ground. So we'll ignore that for now. The man fires a gun, and the bullet moves at the velocity of 350 east relative to the train. So that's going to be V2F. We're looking for V1F, the velocity of the gun. But we'll put a little star by that because we understand when we solve for V1F, it's not going to be relative to the ground. It's going to be relative to the train. So it's not quite what we're looking for, but it's what we're looking for in the short term here. Pi equals Pf. The initial momentum relative to the ground is not zero, right? Because the gun and the bullet are moving relative to the ground. But relative to the train, they're not. They're at rest inside the train. So relative to the train, the initial momentum would be zero. M1 would be 15 kilograms. V1F is what we're looking for. M2 is 0.050 kilograms. You could actually go grams here as well, just like you could go kilometers per hour in conservation of momentum, because the units cancel out. But you got to be consistent. We've either got to convert the kilograms to grams or the grams to kilograms. V2F is 350. When we solve for V1F, it should work out to be negative 1.1667. Now remember, that's relative to the train. But we don't want to find the velocity relative to the train. We're going to find it relative to the ground. So how do we do this? Well, let me give you a little analogy here, okay? It might be a little bit easier for you to kind of visualize than the gun moving backwards on a train here. Maria, is there a question before I? I'm sorry, say it again. You good? Okay. Here's the analogy. All of you guys have probably done this before. You're on that moving walkway at the airport. You're going to catch your plane. Okay. There's a big wide hallway, and then they have a moving walkway that lasts for, I don't know, 100 meters, let's say. Probably not 100 meters, probably more like 50 meters. And why they have that, I'm not sure. You got to walk like 6 miles in the airport, and then they give you a little bit of a break for like 50 meters. Like, do it the whole way. That's what I say. Do the moving walkway the whole way. But they don't. Okay? I don't know. Maybe it's to entertain kids or something, and people like me. I go on that moving walkway all the time. Sometimes I run backwards on the moving walkway if it's not busy. Okay, it's to kill time. But I always go on it here. Let's say the speed of that moving walkway, the walkway itself, let's say is 2 meters per second. I don't know what it is. It's probably 2 meters per second, let's say. There's a store over here. Okay, it's a convenience store. Right? They sell magazines and books and Coke or whatever to entertain you while you're waiting for your plane. Let's say you get on this moving walkway right here, okay? And you don't stand there. You walk on the moving walkway. If you walk on the moving walkway at, let's say, 1 meter per second, relative to the moving walkway, right? Okay, you can walk, 1 meter per second is pretty slow walk, by the way, but let's say that's how fast you're walking. You can walk on the ground at 1 meter per second. Well, you can walk on the moving walkway at 1 meter per second as well. You know intuitively that when you walk on that walkway at 1 meter per second, you actually go past this store at more than 1 meter per second, right? How fast do you go past that store at? 3 meters per second, right? Does that make sense? Okay, we've all experienced that on an escalator, right? If not on the moving walkway at the airport, everybody's done it on the escalator at South Center Mall or something like that, where you're walking up the escalator and you're going faster, right? Relative to the ground, you're going faster. But what if the moving walkway is going this way, and I decide I'm going to walk this way at 1 meter per second? How fast am I going now relative to the ground? Right? Walkway is coming towards me here. I'm walking at 1 meter per second this way. Okay? Relative to the walkway, it's still 1. But what am I moving relative to the ground? Relative to that store right there, what am I moving? My resultant velocity would still be 1 meter per second this way, right? When we combine those, 2 plus negative 1 gives me 1 meter per second. Does that make sense? If I was walking at 2 meters per second against the moving walkway, what would happen to me? My velocity relative to the ground would be 0. Relative to the walkway, it's 2 still. Relative to the ground, it's 0. Okay, so here we are with the train and the gun. Okay, the train is moving to the east. Okay, relative to the train, the gun is moving backwards. So the train is moving forward. Relative to the train, the gun is moving backwards. So what do? How do we find the velocity relative to the ground? It's like this one, right? The train is moving this way. The gun is moving this way. I subtract them. So the velocity relative to the ground would be 75 kilometers per hour. The velocity of the train minus 1.1667 meters per second. 75 kilometers per hour, by the way, is 20.833 meters per second. I subtract 1.6667 meters per second, gives me 19.666 or 19.7 meters per second. Make sense? All right, guys, we're going to assign some more homework for you. Page 486, number 1 to 10. There is a good question number 11 as well, but we're actually going to do question number 11 right now as a group here. So questions 1 to 10 are going to be homework for you, okay? Question number 11 relates to the whole elastic, inelastic thing that we looked at last week. We'll do this one as a group, okay? This is a 220-kilogram bumper car, which is car A, going north at 0.565. It's another bumper car and rebounds at 0.482 to the south. So let's draw attention to the directions here. One's going north, one's going south. Do that in red, though. One's going north, one's going south. Bumper car B was initially traveling south, and after the collision was traveling north. So we get directions all over the place here. You know what? Because there's so many different directions, whatever, I'm going to write down my givens off to the side here. Again, like I mentioned to you before, just to keep it neat. Sometimes I might want to do that. Oh, wait a sec. What do we know about bumper car A and bumper car B? Oh, I almost made a mistake here. I'm thinking, oh, these two bumper cars are going to be the same mass, right? They're going to cancel out. But I forgot about the person inside the bumper car, which is probably a different mass. We want to find mass of bumper car B. Mass 1, 220 kilograms. Oops, that's a heavy bumper car right there. 220 kilograms. M2 is unknown. We're going to say V1I, okay, is 0.565 meters per second. V1F, okay, V1 rebounds, mass number 1 rebounds at 0.482 to the south. Bumper car B was traveling to the south at 0.447. We're going to say V2I is negative 0.447, negative because it's to the south. V2F is 0.395. Could we do question B right now? We have all the speeds, right? Could we do question B? Devin, just put it away, okay? Could we find the initial and the final kinetic energy of this system for question B? We have all the speeds. We're missing something, though. What are we missing? What do we need in addition to speed to find kinetic energy? Mass 2, right? We don't have it. So let's do A first. Let's solve this as a conservation of momentum problem first. But usually we're solving for velocity with one of these questions, but this time we're solving for mass. No big one. Let's plug our numbers in here. M1 is 220. V1I is 0.565. Plus M2, don't know what that is. V2I is negative 0.447. V1F is negative 0.482. plus M2 times 0.395. Oh, we got a problem here. M2 is in two places. How do we deal with that? This goes back to like grade 7 math or something like that. Combine like terms. Right? Let's combine our numbers first of all. Okay, let's take the 220 and the 0.565, combine it with the 220 and the 0.482. So let's do that. Let's pull out the calculator here and let's do that as a group here. Say 220 times 0.565. 124.3. Let's take this term to the other side by adding, because it's a negative term on the right-hand side. So let's take it to the other side by adding. Let's add to 124.3, 220 times 0.482. That gives me 230.34. Now let's take this term and combine them. Since we took the numbers without the M2 to the left side, let's take the other ones to the right side. How do you combine 0.395 M2 and 0.447 M2? This one's negative. Let's take it to the right side by adding 0.395 plus 0.447. 0.395 plus 0.447 gives me 0.842, positive 0.842 M2. So it's not crazy hard. Look, you're solving for M and it's in two places, combine them. If it was 2M and 3M, they'd combine to give me 5M. So if it's 0.395 and 0.447M, then let's just combine them to make it 0.842. All right, now it's easy, right? Now it's going to be 230.34 divided by 0.842 gives me a mass of 273.563. Which rounds to 3 digits, 274 kilograms. All right, now let's find out if the collision is elastic or not. To find out if it's elastic, we've got to calculate EKI and EKF. Do not set them equal to each other. Do not set EKI equal EKF, because we're trying to find out if they're equal. We don't know if they're equal. So 1/2 of M1V1I squared, 220 times 0.565. M2 is we found was 273.563 times V2I 0.447. Hey, why did I drop the negative there in front of the 0.447? Because it's a scalar, right? We needed that with momentum, but not with kinetic energy. Let's get a number for that now. I get to 3 digits, 62.4 joules. Yes? Anybody else have that? EKF, 1/2 M1 V1F squared plus 1/2 M2 V2F squared. V1F was 0.482. Don't forget to square it. And V2F is 0.395. Don't forget to square that either. Okay, so elastic or inelastic? Kirsten, elastic or inelastic? Caitlin, elastic or inelastic? Yes. Why? Good. Kinetic energy was lost. If it stayed the same, it's elastic. If kinetic energy is lost, it's inelastic. Got it? All right, now these two objects bounce apart, right? So by bouncing apart, we couldn't draw any conclusions from that. It could be elastic, it could be inelastic. We calculated it, turned out to be inelastic. If they stuck together, would we have had to go through this process? No, Caitlin, because they would have been inelastic. We would know for sure if they stick together that kinetic energy would be lost. It's inelastic. Okay?